So in this part of the Advanced Experimental Techniques lectures on noise, we're going to think a little bit about what we might actually be able to go and do when we realise we have noise in a measurement system. So we're going to talk about ways you can go and deal with noise. So first of all, think about tracing noise, where we might be picking up noise from, and we're going to look at a kind of archetypal experiment going from the sample through to the main supply, and think about ways of identifying noise types, and then ways you might go and try and mitigate for those. So we're going to look here at a type of experiment. So this here, we're imagining we're doing some kind of electrical experiment on a piece of material, which is our grey slab in the picture here. And so first of all, you think about how are you actually contacting and mounting that sample. So think immediately, how does that sample interact with your experimental equipment? So there you're looking at things like the contact wires, and particularly whether you have things like high contact resistances, how much current is going to be passing through it. If you're going to be measuring at some AC frequencies, do you need to be thinking about impedance matching? If you've introduced some loops, are those going to be a problem? Are you going to be, for example, introducing some inductive pickup? You've got little loops of wire involved there. Or have you got connections between signal lines that you weren't expecting because they're going through on your sample in a way that wasn't planned? You also want to think a little bit about the actual mounting of the sample in terms of the signal lines. For example, where you have a right-angled corner, you can get that's going to help with increasing the induction of the lines. You want to think about how close they are. So are you going to get pickup? Are you going to get capacitive pickup between parallel lines in your actual measurement rig? That's going to perhaps, for example, give you problems if you're doing a high frequency measurement. I mean, remember again that you've got to think about the characteristic impedance. And if you get that wrong, you're going to end up filtering your own signals out. So, for example, one of the very common things is that you're designing a system to measure a high resistance sample, and then you have to remember that the capacitance plus the resistance of your sample make a rather nice filter, and that's going to limit the bandwidth you can use to do your measurement with. So you have to go and think really carefully about the combination of the measurement apparatus plus your sample in terms of its electrical performance. Okay, so then we go and we have our sample mounted, and after that we're going to have some kind of cabling. So there you might want to think, well, are these going to need twisted pairs of cables? Should they be shielding? Do you use particular coaxial cables? Again, if you're doing a measurement at high frequencies, then you need to be thinking about whether those cables are going to be able to transmit the signals you're interested in without having spurious reflections. And you can get reflections from things like sharp bends in a cable. So you have to worry about the radius of curvature of your signal lines if you're up at a high frequency type of connection. And then again, the end of your cables, you want to think about how they actually connected onto the next part of the apparatus. So again, you'll worry about things about impedance matching. Every time you go and change material, you have to think about whether there's going to be a thermal EMF generated across that connection, and is that going to be a problem? How are you going to avoid that, or null it out if you can't avoid it? And there's a few kind of gotchas. I mean, in my line of work in low temperature physics, one of the very common ones is that solder superconducts, and when a material superconducts, it doesn't transmit heat very effectively. So as you cool your sample down, typically, because your sample is mounted on an insulator, you're relying on it being cooled by the signal lines, but then your solder goes superconducting and all of a sudden your sample stops cooling. Or else you generate additional voltages because you've got contact resistances in there that are not linear or are temperature dependent. So there's all these different effects that can potentially come in to mess your experiment up. And everywhere you're introducing a higher resistance, of course, you're adding shot noise, you're adding Johnson noise in. And every time you have an insulating tunnel barrier there, you've potentially got shot noise being introduced. Okay, so we then plug our cables into some electronics. Normally you've got some kind of adapter box or breakout box that's going to take the connectors from your experimental apparatus and then feed them into whatever your measurement system is. And then you need to think, well, are those grounded correctly? Is the box screened correctly? If you've got, say, some electronic components in there, can they be adding parasitic feedback back into your measurement? So again, one of the problems you can have is your measurement electronics can naturally produce some oscillating currents. Those can then be feeding noise into the experiment, which you're then picking up as you're trying to measure. So you need to think about whether you need to be filtering the signal lines to get rid of these parasitic effects, to stop using additional feedback. You can get coupling within your electronics boxes. So, for example, you could get capacitive or inductive pickup from inside your electronics that you need to check you don't have. And then a really big problem you often have is that if you're doing a measurement with several different bits of apparatus, they're all got various grounds associated with them. And then you have to ask questions, well, are these the same ground? So, for example, in this example, we've got one ground which is associated with that amplifier. We've got one ground which is associated with the breakout box. We've got another ground which is associated with the power supply. And then just to cap it all, when we go onto the 50 Hertz main supply, then you have another ground, which is the mains ground. And so these may not necessarily all be at exactly the same potential. So for example, the earth in the mains is only connected to what you might call a real ground, as in something that's actually going into the surface of the earth, at a distribution board, which could be tens of meters away from where you're doing the experiment. Meanwhile, your equipment probably has a ground that's connected to its case. That case, you might connect all those grounds together and then connect it to, say, a water pipe or the metalwork of your building. But then is the metalwork of your building at the same potential as the ground on the earth mains? And even if you don't do that, even if you tie the equipment back to the mains earth, what about the grounds on the actual sample measurement apparatus? And again, are those necessarily connected to ground? And again, I mean, you see here we've got 3 lines joining between our sample and the equipment. So if all of those were shielded cables with the ground and they were connected, the grounds were all connected together at the sample end, then you really mustn't have them connected at the electronics end, your measurement electronics end, because otherwise you've just created a couple of nice ground loops, which you don't want, because the ground loop like that will go and have an inductive pickup and will therefore generate voltages in what should be an earthed signal. And that will then affect your screening properties. So there's lots of scope if you're not careful about drawing out a nice circuit diagram and thinking about how everything goes together, that you can introduce additional noise sources without really meaning to. On the point of connections, connections are often a source of noise problems, and there's a couple of ways that they can introduce noise. So first of all, if they've got different materials, then you can, and you've got a temperature gradient, then you've got a thermal EMF there, and that can fluctuate and therefore give you a source of noise. If it's gets a bit damp, and especially if it gets a little bit salty and damp, then you can set up an electrolytic cell, and you can generate voltages like that, and you can also cause your electrodes to start corroding. If your electrodes have some surface oxide on them, then you have a potential barrier, and now you're starting to think about electrons tunneling across a potential barrier, so you're introducing shot noise. So in all these different ways, you can end up introducing additional noise into your measurement unintentionally. And then as you go across the connector, you also want to think about, it's not just the signal line that has to connect through, but also are you connecting the ground or the shielding through? Because if you introduce a bad connection on some ground line, then you're not necessarily going to be not having a well-defined ground on your experiment, because it's now got a big resistance. And the point about a ground is it should be the lowest resistance path you can get that discharges any electric fields or electric charge that builds up back down to the earth. So again, high quality cabling and high quality connectors can make a substantial improvement on your measurements. So kind of the golden rule is that you can't possibly hope to go and fix noise problems if you don't know what's generating your noise. So again, with a complicated rig, you might well, complicated set of experiments, you might well end up having to strip back things and build it up carefully and make sure you're identifying exactly when and what stage you're introducing noise in. And then you can also think about how you can diagnose the different types of noise. So for example, if you see something which is temperature dependent, going to the square root of the temperature, then you know it's Johnson-Nyquist noise. So then, for example, you're looking for high resistances in places where you weren't expecting there to be high resistances. So if you see a temperature dependent noise, then you think, oh, okay, right, Johnson-Nyquist noise, let's check that all the connections, for example, that should be low resistance are low resistance. Check that all the cables have a low resistance where you're expecting them to have a low resistance. If you get something where the noise gets appears when you start passing a current or biasing your device, then that's a good sign you've got a shot noise problem. So this shot noise, because it depends on the average current that's passing through the contact with the thing you're trying to measure, disappears when there is no average current. So that's the thing you can go and look for and test for. And if you see that you've got shot noise problems, then again you want to think about, well, where, first of all, am I using too small a signal that I'm getting individual events? Is there a possibility that we could say do the measurement with a smaller bandwidth, a longer measurement, so that you can reduce that kind of shot noise? It'll also help with Johnson noise. Can you do things to remove where the tunnel barriers are in your measurement? And then you can also look for inductive noise, and that's something which will scale with the frequency. So it will go and get worse if you run at higher frequencies. In those cases, you're looking to say, well, can I go and screen out the cables? Can I make sure my sample is covered so it's not picking up signals from the environment? Particularly, this is one which can happen where if you are doing an AC measurement technique, then an easy test to go and do is see whether your signal is scaling with the AC frequency you're using, and that would be a strong indicator of an inductive problem in your setup. So by some relatively simple checks of checking with frequency, checking with bias, checking with temperature, you can do a big step to trace where your noise is being generated, and therefore think about an appropriate way of fixing it. One example you might sometimes say, this is particularly common in something like a transistor, but definitely where you have a kind of bistable state, you can see what's called random telegraph noise. So typically this is where your sample can occupy two levels, and what you see is spontaneous switching between your two levels. Again, so this is not got a single source, but it's often related to the shot noise effects, or else various defects and impurities in semiconductors in particular. So it's a phenomenon where a sort of a shot noise event can then go and cause your system to switch state. So if you get a signal which seems to have got random transitions backwards like this, then you're probably looking at some form of random telegraph noise. And again, to go and fix it, well, you might be able to just simply improve the measurement. Alternatively, you might be able to go and look at, say, histogramming your output and recognizing the bistable state, and that might help. You can either decide which state you want to measure, or you can at least understand what's going in terms of what's going on. So these are all kind of things to be thinking about and trying to work out if you're seeing a noisy signal. So kind of the first thing when you're doing the experiment is trying to evaluate whether you're seeing more noise than you might reasonably expect. And then if you are, you want to be looking at ways in which you can identify what's causing it, and that will be the thing that will let you fix it. So your friends for doing all of these sorts of tests and measurements, well, two things principally, obviously the oscilloscope, particularly if it's one that can go and do a Fourier transform of the signals. You can look at the frequencies, because there's often really useful information if you look at the different frequencies in the signal. You can decide on the basis of that what the likely source is. So for example, at one stage we were doing a measurement in the lab, and we saw things were being a bit noisy, and when we looked at the Fourier transform of it, we realized that it was coming up every 5 hertz. And then we sort of read through the manuals of all our equipment and realized that our temperature sensor was reversing the bias on the temperature sensor every 5 hertz. And it was doing that deliberately to go and remove the thermal EMFs that you might get. The problem was that because it was doing this continuously, it was then adding a 5 hertz square wave into our measurement. And then that showed up not just at 5 hertz, but every multiple of 5 hertz up to about 250 hertz. But once we had identified that that was the problem, we were then able to do something about it, and we were able to go and program the temperature controller so it would turn off the reversal for the short period of time that we were going to go and do the measurement, the electrical measurement, and then we would turn it back on again so that we could go and do the temperature measurements reliably. And so we were able to bypass or defeat the noise source like that. But we were only able to see that because we were able to put it into an oscilloscope and then look at the frequencies we had coming up available. And then the other key instrument, of course, is your multimeter, which can, if it's a decent multimeter, not only tell you the voltages, both AC and DC, it might be able to tell you the frequency of the AC voltages, it will also tell you resistances. And whilst you probably don't really want to be measuring your actual sample with a handheld multimeter, because you don't really know what it's going to, how much current it's going to use to go and do the measurements. If what you want to do is to measure your cables to make sure that your cables got good contacts where you expect them, and that things aren't shorted together when you didn't expect them, then it's the invaluable tool to have to hand. The other thing to say, of course, is that it doesn't matter how good you are at identifying the source. If your actual experiment is not well designed and not securely built, then you're going to have problems no matter what. And again, nearly always the problems end up in cabling. You know, if you have a problem, before you start thinking that your meters are broken, your hardware is broken, you want to first of all check that the cables are good, because the cables are always the vulnerable part of an experiment. The cables flex, so they tend to break connectors. They're liable to be pulled around. They're liable to be laid out in ways that aren't great. And in extreme cases, they get stood on, they get broken. Very, very bad for cables if they get put in too tight a bend, because you tend to break the insulation, or worse, break the conductors. And so if you look carefully at a cable, you want to, you know, if you've got a problem, check your cables carefully, check that the connectors are on securely and that there's no obvious sign of a break. So generally speaking, you can undo a cable and you can go and actually look at how the cables are soldered into the connector and just check that they're mechanically strong. So if a soldered joint is mechanically strong, it's almost certainly good electrically. And then check for physical damage on the cable, on the cabling itself. And then you can go and check with a multimeter that things conduct all the way through. So pretty much the first thing you always want to go and do is try changing your cables over and see if that makes things better before you start disputing what's going on. And again, likewise, be thinking about connectors. You know, a cheap and cheerful connector might work, or it might just go and give you a spurious noise source. So if you do all of those things and you still have noise, well, what can you do about it? So now we're into the territory of filtering and averaging. So obviously averaging is kind of something you've been taught to go and do since before first year labs. So the key things for averaging to work is obviously you have to have repeated measurements, but they also have to be independent measurements and uncorrelated. So that means that the measurements should not depend on the history of the sample or the measurement. So every measurement you repeat to make the average should be entirely independent, not a function of what happened previously. So if you do have uncorrelated measurements, then they should follow counting statistics. So that means if you go and repeat a measurement many, many times over, what you'll find is that the mean and the standard deviation should be consistent, but the standard error in your mean, so in other words, what you quote as your uncertainty, that should scale as the standard deviation divided by the square root of the number of samples, and that will go down with the more samples you do. But of course, because it's going down as the square root of the samples, in order to make a 10-fold improvement in your uncertainty, you have to take 100 times longer. And to make 1,000 times improvement in your measurement, you have to take 1,000,000 times more measurements. So the plot here, I've just gone and calculated a set of random numbers and gone from 10 random numbers to 1,000,000 random numbers and worked out the mean and the standard deviation and the standard error across all of them. And in order to make it comparable, I've just increased the frequency for the of all the numbers. We've got 1,000,000 counts. It's just that they're only got 10 values, 100 values, and so on. So what you see is that the blue bars, which are the smallest sample size, are the least looking like a normal distribution, whereas the purple bars, which are the million counts, is most like a normal distribution. But if you look at the mean in the blue line and the standard deviation in the red line, yeah, okay, the standard deviation, they both fluctuate a little bit to start with, but then they get level and they're very consistent, whereas the standard error, obviously on this log scale, decreases consistently. But of course, it's not always feasible to just go and average like crazy. That adds time to your measurement, and then you need to worry about whether your experimental environment is going to be the same over the entire length of the averaging, as well as whether you can actually get the measurement done in the required time. So some of the ways around that people do this is get into the ideas of filtering. And so kind of the simplest thing is to do an adjacent average smoothing. So what you do here is you say take 10 points and you average them, and you record that value, and then you take you shift over by 1 point and take points 2 to 11 and average them, and then points 3 to 12 and average them, and 4 to 13 and average them, and so on, and gradually build up that way. And so every single point you're then working with is composed of the average of several points. So this is a well-known thing in finance. This data is in fact a local exchangeable currency, the Leeds dollar, and its value in GP pounds over the course of a year, or just under a year, and with different levels of averaging applied. And so you're able to see that as you increase the number of samples you use to make that average up, then it gradually gets smoother and smoother and smoother. Of course, the problem then happens as you get towards the end of your sample, the number of data points you have runs out. However, such approaches are also now increasingly well known in other fields. So this topically is the COVID-19 infection rate for the UK, and at some point they decided to introduce a 7-day rolling average, which is exactly this idea. So the problem here is that the infection rates were being reported primarily during the working week. So at the weekends, you had a lower infection rate. That wasn't that people weren't getting infected, it's just that we weren't recording it then because people said, oh, I'll leave it till Monday to report them. And so it could look like, if you look day by day, that you had sudden drops and sudden increases. And of course, that's not really real at all. And so they introduced the 7-day rolling averages. And then you'll notice that right on the right-hand side, the 7-day rolling average stops a few days short of the last bit of data. And that, of course, is because you can't work out what the 7-day rolling average today is, because you need to know what's going to be, what the actual number is going to be tomorrow, the day after, and the day after that. And so you always have a bit of a lag, and you either end up plotting the data with that lag, or else you end up with data missing at the most recent time period. And again, this is always something that you have to worry about with any kind of averaging, smoothing, or filtering process, is how do you handle the start and the stop of your data? Because you don't have data before you started, and you don't have data after you stopped. So any kind of filtering process is going to be susceptible to that. So it's worth actually talking a little bit about what's going on with this kind of an averaging, rolling average, because this is in fact a simple form of filtering. So as I said, what we're doing is we're taking a block of a window of the data. So in this case, I've got 4 data points, and I record the average of that. And then I move to the next 4 data points and record the average of that, and the next 4 data points and record the average of that, and so on. Mathematically, what we're actually doing there is we're convoluting the data we sampled with a windowing function. So in this case, the windowing function is something that is zeros and then a block of ones and then zeros again, meaning that we don't count any of the data before we are averaging window. We then count all the data in the averaging window equally, and then we ignore the rest of the data there. So you've probably done a little bit about convolution in Maths 4. We don't actually need to know about the maths particularly for this. In terms of thinking about in terms of what this is doing to our data, we can think about what happens when we do the Fourier transform and look at the frequencies. So this relies on a rather nice property of convoluting functions, and that is that if I convolute 2 functions together and then take the Fourier transform, then what I get is the product of multiplying the Fourier transforms of those 2 functions separately. So if I think about what's going on in frequency space, then I've got some kind of signal which has a typical background frequency spectrum like we showed in the previous video, with in red the signal we're interested in. And then the Fourier transform of a function like this, a square top hat function, is basically a sinc function. I'm actually looking at its magnitude here. And so the result of the convolution is the same as if I multiply those 2 Fourier transforms together. So if I do that, then what's going to look like is something a bit like this. So I've changed the frequencies in my signal by multiplying it by the Fourier transform of the filter. That's the effect of the filter, is to suppress those high frequencies. The problem is that we're not really suppressing the frequencies quite ideally. I mean, what we'd like to go and do is simply just say, keep the frequencies below some threshold and get rid of everything else above that threshold. So we get rid of the high frequency noise and we keep just the bits of the signal we're interested in. But what's actually going on here is, yes, okay, we've reduced the higher frequencies, but then because of the shape of the Fourier transform of the filter, it's actually reintroducing some high frequencies again. And so you get these distortions in the signal, which are coming from the filtering. It's a sort of aliasing effect almost in the filtering, that the effect of the filter isn't to just suppress the high frequency, it comes back again. Okay, so, well, what could we do about that? So one of the common approaches is, rather than using a function just adds the values of the data points in the window equally, we do something a little bit more sophisticated and we weight the different data points differently. So in the picture here, I've shown this by having a kind of continuous shade of green from the white at the outside edges, meaning we don't really count those data points at all, to the ones in the middle that we pay most attention to, in order to work out the average value for that window. So again, in terms of the maths, what you'd be doing is, you say, multiplying by something which wasn't a top hat, but by something which is maybe more like some kind of triangular signal, or possibly even more like a sinc function itself. And the reason you do that is you're looking for a windowing function, a weighting you apply when averaging this data, that's going to have a nicer Fourier transform. So in this case, if we made that filtering function really look like a sinc function, then the Fourier transform of sinc is a top hat. And now what this is telling us is we're going to have the same noise spectrum with the signal that we had previously, but now we're going to multiply it by something which is basically 1 for low values of frequency, and then immediately goes down to 0 and cuts off all the higher frequencies. And so the signal you get is doesn't have that kind of distortion of the high frequencies coming back in. It's a much better behaved signal. Now, of course, the issue is that you can't really go and get quite such a nice abrupt shutdown, but there are different types of signal filtering options, and these can be implemented in hardware or they can be implemented in software that will go and give a nice frequency response and not reintroduce unwanted frequencies into your measurement. So in software, I mean, you can always have a look at the, for example, in Python, at the scipy.signal module, which has a whole slew of different functions. And some of these software functions are actually emulating what various hardware circuits would do. So by getting the right combination of inductors and capacitors and resistors, you can build a filter network that will give you some desirable frequency response. So it's, again, an appreciation that you can actually analyze your noise suppression algorithms with kind of the maths that are actually part of your undergraduate course.